I'm in the process of trying to repair and restore this Osborne OCC1 vintage computer. In the videos so far in this series, I've stripped the system down, gone through the drives, cleaned them, lubricated them, got them freed up, and been through the power supply, replaced the failed caps, and given the system an overall inspection and carried out some repairs on the keyboard. And where it is at the moment, it boots to the welcome screen, but it won't boot from the floppy disk. I'll show you what it does. This button here, I've got it hooked up to simulate the return key being pressed. Just makes it easier to run these tests without having to have the keyboard in the way. So if I operate this, you'll see that the drive light will come on. You can hear the drive doing its thing. And then it stops, and the system is now non-responsive until we press the reset key. So it's obviously doing something. Now it does this irrespective of which of the two drives I try to boot from. So if I put the boot disk, this is supposed to be a working boot disk. I don't know if it's a good disk. I've got a feeling it probably is. But if I put this disk into the second drive and try to boot from that drive, it does exactly the same thing. So it's doing something. It's not coming up with an error message, which is a bit strange, but not necessarily that surprising. What I'll do now is take the disk out, and I'm going to put a non-boot disk in. So this is just a random disk. It does have some data on it, but it's not a boot disk for this machine. Okay, and we'll try and boot the machine again. I'll press reset, and then we'll try to boot back up. You'll notice we're now getting a boot error message, and it'll keep doing this now till I stop it by pressing the reset button. So clearly it's trying to go through the boot process. It does seem to be capable of reading data from the disk, and in fact in the previous video we had a look at the data coming out using a scope, and it seems to be okay. What we're going to do in this video is go through one possible method of fault finding with this machine. There's any number of ways you could go about this. It would be nice if we had direct access to the RAM chips. I still feel this might be an issue with RAM, but could be a fault anywhere else, of course. The method I'm going to use in this video is to use the logic analyzer to try to walk our way through the boot up code and see exactly where it's failing. It's clearly doing something, but it's not booting. I suspect it's loading the system from the floppy disk, but then when it hands control to the system, that's the point at which it's failing. But we'll try and get a better idea as to what's going on and see if we can make any headway without starting to tear the system apart. So I'll be using my Agilent 1680 AD logic analyzer. I've got it hooked up to the CPU. It's a Z80, of course, and what we can do now is start looking at the boot code. There isn't much boot code or monitor code in this machine. There is a monitor ROM, but it's fairly small, very basic. It doesn't really have any commands really that would help us in testing the RAM. Which would be nice if it had some capability built into the ROM for us to read and write values to the RAM. It would make things much easier. So before we get started, just a quick look at what the system should be doing when we try to boot from floppy disk. So this is the memory arrangement for this system, and you can see that it's mapped into 3 banks. We've got bank 1, 2 and 3. Bank 1 is effectively our RAM, and bank 2 is a kind of shadow. A lot of it's a shadow of the top part of RAM, and the bottom part is used for mapping the in-out port and also the monitor ROM. So when the system starts up, it resets to bank 2 and starts executing code at the bottom of this ROM. And that's the code that's responsible for putting this message onto the screen and handling the key presses. So we can see this is working and that the system can access the ROM. I'll reset it again, Anytime we carry out any commands and press a key, you'll see the screen flickering, and that's because the system, the monitor ROM, is trying to process the key press. And so we know that the monitor's most likely running, and it's not crashing, it keeps going, so chances are that there's nothing actually wrong with that. Could be a problem with the mapping, of course, but that's again fairly unlikely because the disk drives are being accessed, and also the display itself is working. So again, the video display is working, so chances are this is working. It doesn't necessarily mean that the mapping is working, but it does give us a fair indication that at least a large proportion of the machine is functional. So what should happen when we hit the return key is the code in the ROM should cause the disk drive to be accessed, and on the disk the system, this has got double density drives and the double density adapter board, and the firmware in the ROM detects the type of drive, whether it's single density or double density, and it uses that information to determine how to make sense of the data that's on the floppy disk, because it does vary with the two. The information's the same, but the way it's arranged on the disk is slightly different on the two types of disk. So what should happen when we press the return key is the code in the ROM should copy the data from the first few tracks on the floppy disk into this area of RAM. So it copies across the CCP, which is the console control RAM, the BDOS, which is the basic disk operating system, and the BIOS, which is the basic in-out system. So it copies this code into this area. So it copies it from a CB00, that's for the BDOS and CCP, and from E100 for the BIOS, and it then hands control to this to start up the operating system. So we need to check to see if this is actually occurring, and unfortunately I don't have much information about this system, and while CPM is fairly consistent as far as the core code is concerned, the specific implementations can vary slightly, and so I don't really know what the first few bytes in the two blocks should be. Otherwise we could just look at it and see what's actually being loaded, if anything. So we'll have to do this the hard way. We'll start looking at the system boot up sequence, and we'll try and figure out exactly what's going on. Now luckily the technical documentation for this system does include a listing for the monitor ROM. So I've printed off the relevant sections of this. It's not particularly big, but I've just printed off the few pages that we need to concern ourselves with here. If you want to play along, this is the 1982 Osborne technical document for the OCC1 computer, and you can do a search for that using Google and download a copy. And this comes out of the 1.4 version ROM at the back of that document. So I've had a look through this to figure out where to get started. We know the system is basically running, so we don't need to go right back to the beginning. What we're interested in is the boot sequence. So if we look through, and we can start here, and the only complication in doing this is ideally we'd like to trigger on these addresses for our, trigger our analyzer on these addresses. But because of the way this code was either compiled or decompiled to create this, there's a mismatch between these addresses and what is actually in the ROM, and it's not consistent. It changes. Sometimes it's 6 bytes, sometimes it's 16 bytes. So you need to take that into account. What I did is I actually took out the ROM, read the ROM, and then I used that to determine exactly what the offsets were for each individual section. So that's just something to take into account. If you try and trigger on the address as it's written here, you'll get different values because you're not actually at this point, you're somewhere else. But the code itself is the same. The actual instructions are in the same order. and it's not an error in the ROM because the jump addresses are correct as well. So here where we have an address for as a destination for a jump, that's correct according to these values, but it's also different when we capture the data, so it's not like there's a mismatch, it's just that there's an offset. Okay, so if we read through this, we'll see that if we get to this point, this is address 0255, these are all hex of course, and we have a call here to home the drive, so it sends the drive back to the home position. It determines the density, so it reads the density, and as long as that was fine and no errors reported, it carries on. It will throw up an error message if that's not right, and then it will carry on. And what it starts off doing is it will read the first sector, and then it will check the first 2 bytes. The first thing it's reading is the CCP, and it checks the first 2 bytes of the CCP it's read from the floppy disk, and if either of those 2 bytes are wrong, it throws up an error message. So we'll start at that point. We'll get the analyzer switched on. We'll set up to trigger on a fail. What I'll do is I'll put the wrong disk in, and this should then fail because this data will be incorrect. And as long as we can capture the jump to the error, we'll know that our setup is correct, and then we'll put the correct disk in and see if it can get past that error, and that will tell us if it can successfully read the disk and if the disk is valid, and also if our assumptions and setup are working. And if everything goes well, we can then carry on and work our way through the rest of the code. I've got the analyzer set up for the Z80. All the pins are connected so we can monitor anything we want to. And looking at the code, we're going to start by triggering at this point here. Now this is where it's read the first sector off the floppy disk. It should be reading the CCP from floppy disk, and so what it now does is it checks the first 2 bytes. So where we're triggering here is if it gets to this point, the first byte that it read is correct. So I've got the analyzer set up to trigger on 0280. The source code shows 027F. There is an error, as I said, an offset here, and the offset at this point in the code is F. So all we need to do is add a value of F to the address shown in the source code, and that will give us the actual address in ROM. So I've got that set as a trigger, and what we can now do is hit my little switch, and that will start the machine trying to boot. The disk I have in at the moment is not a proper boot disk, it's just a random disk, and so this should actually fail. It should jump to an error at this point. It shouldn't jump through or shouldn't fall through and continue, so we shouldn't actually get here. So I'll arm the analyzer, we'll hit the switch, okay. As you can see, the analyzer is not being triggered. The system is just going round and round, and it's displaying the boot error on the display. So I'll press the reset button on the Osborne, and we'll stop the analyzer. So clearly we're not triggering as we should, which means that at this point we're seeing an error. So instead of jumping or falling through to this point, it's jumping through to the error. So this test of the first byte is failing. What I'll do now is put the proper boot disk in, and if the boot disk is correct, and also if the system can correctly read the first part of it, we should end up triggering the analyzer and getting through to this point. So I'll swap the disk over. So we now have the correct floppy disk in. I'll rearm the analyzer, hit the switch, and as you can see, the analyzer has indeed been triggered. So what we can now do is start looking through the code. So notice we're at the correct address. That's what we expected. So that's this 28E address, and the value we should see there is 23. And indeed the value we are seeing is 23. If we go to the next address, 28F, then the value there should be 7E, and if we look at the next byte, it's indeed 7E. So we have successfully got through to this point. So what's happened here is it's read the first sector, it's checked the first byte of that sector, and it's correct. It matches what it's expecting to see. So the next thing we can do is move on and check to see if the second byte it's reading also passes the test. So correcting our address, the value we want to trigger on is 0295. So we'll change the analyzer. I've got a simple trigger set here, so it's just a single event at whatever address we set on the address bus. So 2. Okay, I'll reset the Osborne, rearm the analyzer, and we'll try booting again and see what happens. So as we can see, the analyzer has been successfully triggered. We've captured down at this point, so we now know that both the first 2 bytes in the first sector that it's read are correct. So we can now move on to the next step. So if we continue on to the next page in code, then if we follow it through, we end up at this line. HL, by the way, has already been loaded previously with the destination address for loading the CCP, BDOS and CBIOS. We'll come back to that later on. But we get down to this line, call BCPM, which basically means boot CPM. And if we look through the code, we will find this, and this is the boot CPM. This is where it jumps to. So this is our function to load CPM, and we should end up here at 2A1. If we want to capture this, of course, it's not 2A1. We need to add F to this as well, so the error here is still plus F. I'll just make a note of that. So on all the addresses on this page we need to add F. So if I correct this value, we end up with a value of 2B0. So that's what we want to trigger on now and see if we're successfully jumping to this procedure. So I'll reset the Osborne, rearm the analyzer, hit the switch, and we have successfully triggered. And the value we should see here is of course the first value of 22, which it is, so that's correct. Incidentally, I've been asked how I know which of these blocks to look at for the values, and what I'm looking at here is the read line. So we know that it's read low, so when this goes low, at some point before it goes high again, the value we're looking at should be the value that's been read by the processor. So that's what we're looking at here, in case you're wondering how I know which of these to actually take notice of. So we know we're getting to this point, and we can now start looking down through here. Now I won't go through all this, it will get fairly boring, it's just really repeating what we're doing here. But the point I want to try and get to is where it's read the 3 main blocks. So we need it to have read the CCP, the BDOS and the BIOS from the first 2 tracks, copied that to RAM, and then it should exit and jump to a point where it starts up the main code. So we'll find that in the listing. I'll enter that as the destination address for our trigger for the analyzer, and we'll see what happens when we try and boot. So I went through the rest of that block of code and it repeats 4 times, so it goes around that loop 4 times, so it's reading 4 blocks, which is correct for the type of disk we're using, and then it exits. So this was the call we made to that block of code, so it called BCPM. It's now returned, or at least it should return. It should get to this point and it should then restore or pull off the stack the value into HL, which is the address that it's going to jump to start up the system once it's loaded. So what we can do now is jump or trigger on this point and see if we successfully get back from this call. In fact, what we'll do is we'll come down to this point and check that we're getting this far. So we need to set the analyzer for this point, and again we need to add F to this value to get the correct address. So the corrected value for that address is 02AA, so we'll set that as our target for the analyzer. I'm going to return this to a simple trigger. Okay, we'll reset the Osborne, arm the analyzer, and then hit the switch. And so we have successfully triggered on this point, and just to make sure, the value there should be E9, and as you can see it is indeed E9. So this is the point at which it's going to jump through and in theory should enter the operating system that it's just loaded. So what we'll do, the final part in this video, is we'll scroll across and try and see exactly where it's jumping to, and we're getting a value of E100. And if you recall from earlier in the video, if we consult our memory map, E100 is the start of the BIOS, so that looks correct. That's probably where it's supposed to jump to. From here on, what I need to do is try and locate some information that's going to tell me what values should be there. We've got C3 here. Now that looks fairly normal. That's typically one of the instructions you would find at the beginning of that section of code, but I don't know if it's correct. So I've got C3, F3, E4. So they're the values I'm seeing. Now whether these are correct or not, I'm not yet sure. The next thing I need to check is what values it's supposed to be loading at the beginning of the BIOS for this particular implementation of CPM. So it's clearly getting as far as loading, or thinking it's loading, the values from floppy disk. It thinks it's loading the BIOS, DDoS and the CCP, and it's trying to hand control to the beginning of the BIOS. I don't know if this is where it's failing or if it's now going through this code and crashing further on. The system is crashing, it's not responsive to any key presses beyond this point, so it may well be that this is a RAM or hardware failure that the CCP is not able to deal with. Or it may be getting further than that and crashing further on, but the next thing I want to try and find is the code that it's supposed to be loading. We can then check that, and then from that point on we can start checking to see what it's doing further on, based on what the code is expecting it to do. And if it's then a hardware failure, we should be able to track that down. But either way, it does seem as if though the boot process from the floppy disk is correct. It could still be a floppy disk issue. It might be that the wrong information is on the floppy disk. Seems unlikely based on the fact that it passes the first 2-byte check, but that doesn't necessarily mean that the rest of the data is correct. Okay, so that's it for this video. hope you didn't find that too boring, but this is one fairly powerful technique for fault finding on a machine like this without starting to tear it apart. And we can now effectively move on and continue this process through the rest of the startup sequence once we know what it is we're supposed to be seeing. If you've been through this, if you know what this code should be at the beginning of the CCP or BIOS, then please leave a comment.